We're always talking about things like, I need to lose some weight. We step on a scale and we think about that number. But what if I told you that in the world of physics, your mass and your weight are two totally different concepts? It's probably one of the biggest mix-ups in all of science, and today we're going to clear it up. So let's start with a little thought experiment. Picture this. You've blasted off into space. You've traveled all the way to the moon. You step out of the lander onto that dusty surface, and you feel incredibly light. You can bounce around with hardly any effort. So here's the big question. Have you actually lost any part of yourself? Has your mass changed? Let's dig in. First up, we need to talk about the part of you that is fundamentally absolutely constant. The one thing that stays the same whether you're on Earth, the moon, or floating in the deep void between galaxies. And that constant is your mass. It's really that simple. Mass is just the measure of how much stuff you're made of. It's all the atoms, all the molecules, all the matter that makes you, well, you. And there are three key things to remember about mass. One, it's always constant. Your mass is the same here, on Jupiter, everywhere. Two, we measure it in kilograms. And three, we're talking about its rest mass, which is just a fancy way of saying the mass of an object when it's not moving. Now, mass is also how we measure something called inertia. You ever notice how it's tough to get something really heavy moving from a standstill, or just as hard to stop it once it's going? That resistance to changing what it's doing, that's inertia. And the more mass something has, the more inertia it has. Think about it this way. A huge, loaded truck has a ton of mass, right? So its inertia is massive. It really doesn't want to start moving. But an empty shopping cart? It has very little mass, so you can zip it around the store with almost no effort. It's the exact same principle, just on a totally different scale. Okay, space helmets on. We're leaving Earth behind for a moment. We're on that journey to the moon. And as we land, something is definitely about to change, but it's probably not what you're thinking. So there you are, bouncing on the lunar surface, feeling light as a feather. It's an incredible feeling. But let's pause and think back. Has the amount of stuff that makes you actually changed? No way. Your mass is exactly the same as it was on Earth. So what gives? What has changed? And this brings us to our second big idea. There's another property that's not constant at all. It's a force, and it depends entirely on your location. This is the real reason you feel so light. And that force is called weight. See, weight isn't the stuff you're made of. Weight is the force of gravity pulling on all that stuff. It's a relationship, an interaction between your mass and whatever planet or moon you happen to be standing on. So this is the big difference. Unlike your mass, your weight is absolutely not constant. First off, it's a force. Second, it's measured in a unit called newtons. And third, and this is the important one, it changes depending on how strong gravity is wherever you are. The reason why it changes is because of something called gravitational field strength, which we represent with a little g. You can think of g as a number that tells you how much gravitational muscle a planet has. A bigger planet with more mass is going to have a bigger g. Here on our home turf, Earth's g is about 9.8 newtons for every single kilogram of mass. That's our planet's gravitational signature. But the moon? It's way smaller and has much weaker gravity, so its g value is way, way smaller. And that's exactly why you weigh less there. All right, we've defined our terms, we've been to the moon and back. Now it's time for the main event, a direct side-by-side comparison to make sure this all sticks. If you only remember one thing, make it this. Mass is the matter in you. Weight is the force acting on you. Simple as that. Let's break that down even more. Definition: quantity of matter versus a force due to gravity. Constancy: mass is the same everywhere, but weight changes. The units: kilograms per mass, newtons for weight. And finally, think about the tools we use. To measure mass, you use a balance. It compares your stuff to a known amount of stuff, so it would work anywhere. But to measure weight, you use a force meter, like a spring scale. That spring stretches differently depending on how hard gravity is pulling. And this all comes together in one beautiful, simple formula. Your weight is simply your constant mass multiplied by the local gravitational strength, that little g. This little equation is the key that links these two ideas together.
Let's see it in action. It's super easy. Say you have an object with a mass of 2 kilograms. All you do is multiply that by Earth's g, which is 9.8. You run the numbers, and boom, Its weight on Earth is 19.6 newtons. That's it.
So you might be thinking, okay, this is a neat little physics lesson, but does it really matter in the real world? Well, it turns out that understanding this difference isn't just trivia. It's the difference between success and disaster in some of humanity's biggest endeavors. Think about it. How much fuel does a rocket need to escape Earth's gravity? That all depends on its mass. How strong does a bridge need to be to hold up under the constant pull of traffic? That's all about weight. A crane operator absolutely has to know the weight they're lifting, not just the mass, to avoid a catastrophe. This distinction is literally everywhere. So in the end, it really all boils down to this one simple idea. Mass tells you how much matter is packed inside something. Weight tells you how strongly gravity is pulling on all of that matter. That right there is the key takeaway. And I'll leave you with one final thought. Right now, as you're sitting or standing there, you can feel a force holding you down. So what do you call that force? Is that your mass or is it your weight? After today, you know the answer.